Hey folks, welcome to physics, and the topic we're going to start off with is electricity, partly because of us being on lockdown and a lot of the experiments we can actually do online using simulations. It does mean when we come back to school, we'll get to do some of the more hands-on stuff with the dynamics topic, with forces, and we'll also go back and do some of these electricity experiments. So today we're going to start by looking at static charge, which you may have come across already in second year. So we're going to describe the different types of charge, describe how charges interact, state where the electrons, protons and neutrons are found, so a wee bit of chemistry there for you, and describe what conductors and insulators are. And a lot of this might be revision for you or things that you've come across, but I really want to make sure everybody knows the same stuff. So to get you thinking, why might be a bad idea to play golf when there's a thunderstorm? So have a wee pause, think about it, and then we'll talk about it as best we can. Okay? So you probably noticed there's a wee tree there, and then there's a golfer with a golf club there. And the reason why it's a bad idea is because this may happen. Okay? Obviously, it's not a real photo, it's most likely photoshopped, but you can imagine that the golfer with the golf club stick in the air could attract the lightning and get a massive lightning bolt. So, how does that happen? What is a lightning bolt? What's it made up of? We're going to try and explore these ideas over the next couple of slides and lessons. Now, sadly, at this point, I would bring out the Van de Graaff generator, but we're not in school, so I promise you, when we get back into school, we'll have a wee go at this, and if you've not seen it before, it's really one to look forward to. I'm sure you've seen something like this one before. I won't say anything more, folks. Okay, so if I had the Van de Graaff generator, we would do that, and we talk about how is it that you can get an electric shock. Now, um, if you watch this wee video on the YouTube link, I'll put it on the message board so you can access it. That will show you how you can get an electric shock from an electric fence. It will also show you how to not get an electric shock from an electric fence. Now, a word of warning, obviously those people are professionals, so I don't want you to watch this video and then to try it yourself. It's very, very dangerous. You could hurt yourself very badly, okay? But the key idea is if you want to get an electric shock from an electric fence, is that you must be touching the ground. And that's called earthing yourself. So if we think about the starter question, you can see the golfer there is standing on the ground and the lightning is going straight to the ground through him. So that's why he actually attracts the lightning. It's because he's providing a nice easy path for the electricity to flow from the air through him into the ground. So if you don't want to get an electric shock from a fence, what you can do, and again, don't try it please, is you jump onto the fence and make sure you're not touching the ground. Okay? So let's zoom in a little bit into the physics and let's talk about what static electricity is made up of. Now, first of all, static electricity is electricity that doesn't normally move. It can move, but if you don't do anything to it, it will happily just sit on top of a surface or a material. And it's made up of electric charge. And there are two types of charge that you might have heard of, a positive charge and a negative charge. And that's how I usually write my positives and my negatives. It just saves me having to write the full thing. Okay? We usually think of these charges as being like little snooker balls with a little plus on it to say positive and a little negative on it to remind us it's negative. The colours are usually black for negative and red for positive. And one of the reasons they're chosen for this is because electricians tend to be mostly men, and unfortunately men can become colourblind. So red and black is a colour that you can see even or tell apart even if you are colourblind. Okay, so negative charge is made up of electrons, and again this is how I write my electrons in shorthand. And you can find electrons inside atoms. In fact, you might even know that the atom has electrons on the outside. And in the inside, you have the nucleus, which is made up of a neutron and a proton. And we'll come back to these again later in the year when we start looking at radioactive materials. Right? How does radiation happen? What are the effects of radiation, etc. Now, the next couple of slides are all slides which are to do with little experiments that ordinarily I would have let you do in the class. However, we're not in class, but these are experiments you could probably do yourself at home if you've got the right material. So I'll talk you through it. Feel free to try it. If you want, you could even take photos of the setup for your experiments so I can see you've done them and you can show them to the rest of your class. So the first one is, instead of using a rod, you can use a wee plastic comb or a plastic hairbrush. And if you just rub that hair comb or comb through your hair, you should find you'll charge it, you'll coat it with static electricity, and you should be able to pick up little scraps of paper. So take a photo of that and show me if you're able to do it, folks. I would love to see that. Second experiment is you can take a cloth, preferably sort of like a yellow cloth that you use to kind of polish things, and as you rub that across your comb or any kind of like a plastic ruler, you should be able to do the same thing. You should be able to pick up little bits of paper with it. Another one you could do is if you've got a tap which runs a straight line of water, if you hold a charged comb next to it, you should be able to make the stream of water, provided it's not too thick, to actually deflect and move away. Again, if you can take photos of that, I'd be mega impressed because it's a very nice experiment to do and it's dead easy as well. Okay, third one, another really nice experiment, and I'm sure you must have empty drinks cans at home. Doesn't need to be cola, it could be any kind of soft drink can as well. And you will need a balloon to do this one. So I'm sure you could probably get balloons at Asda or some other kind of party shop, as it were. And what you do is you blow up the balloon. Now, in the past, what I found is you can either rub it against the jumper, and you've probably all done this at a party before, where if you rub the balloon against the jumper, the balloon will stick to the ceiling. Okay, but did you know that if you rub it against your jumper and hold it close to the can, not touching it, you can actually make the can move. Okay, you can make the can either move away or towards the balloon. Now, in fact, the best way to make the balloon charged is actually to rub it against your hair. And if you do that very quickly and for a good length of time, you'll also make your hair stick to the balloon. And again, all of that is to do with the static charge. Okay, and then finally, just to show you, again, you can do the same thing, charge the balloon by rubbing on your hair or on your jumper. You can pick up little scraps of paper with the balloon because the paper will be attracted to the balloon. You can even deflect water with the balloon as well, right? So if you do any of these experiments, show me, take a photo and post it on the message board so we can all see how great those experiments are, folks. Okay, so a wee bit of revision here, and some of you might know this already. If you don't, that's fine. A conductor is basically metals which let charge flow through them easily, e.g. the dome of the Van de Graaff or the copper in your wires. An insulator is a non-metal that does not let charge flow through it easily, but charge can be put onto it, e.g. your plastic rod and your balloons, or the insulation around your wires that connect your electrical devices in the home. So conductors and insulators, you just need to know what those words mean. So we've had a wee look at charges, and we've had a wee look at some of the effects of electrostatic charges, but how does the charge know when to attract or repel? So again, we want to zoom in deeper into the physics and figure out, how does a charge know when it should be attracting something or repelling something? So here's the key thing we need to know, is that unlike charges will attract, so what I mean by that is if you've got two charges that are of the opposite charge, so positive and negative, then they will always attract each other. On the other hand, like charges will repel. So what I mean by that is if they have the same charge, i.e. if they're both negative or both positive, then they will push each other apart. So try and use these words that I've given you. Unlike charges will attract. So that's the key word I want you to try to use. Like charges will repel. So that's another key word I want you to use. So get into the habit of trying to use some of these technical words to describe what's happening, because it'll make it easier for you to answer the questions. Okay, so some of you might be sitting there thinking, well, okay, that's great. I know like charges repel and unlike charges attract, but I haven't really answered, how does it know that? How does a charge know whether it's positive or negative? And how does it know other charges are positive and negative and therefore they attract? So the idea to explain this is something called an electric field. And these are actually very common in physics. You might know of one already. In fact, it's probably the one that makes your feet stick to the ground. I won't say anything more. Okay? But fields are invisible lines around a charge, and they allow them to react in an expected way. So, for example, the fields around a positive charge always push out the way, and then for a negative charge, they always go in the way. And you can see, if I had a negative and a positive charge right next to each other, these field lines could probably join together, and that would tell you they would actually stick together. At the same time, if I had two negative charges next to each other, the field lines would all be pointing in the way, so that means they wouldn't be able to come together because the field lines don't allow them to do that. So that's how we explain how things attract or repel each other, is that there are these field lines which tell them whether they're positive or negative and which direction they should be going. Okay, so a wee bit of MTV for you. See, think, wonder. What else also has fields around them? So we've just told you that negative charges have fields around them. So here's another one. So see, think, wonder. And final one, see, think, wonder. Now, this is meant to represent the Earth. I hope you kind of recognize that. And these fields allow physicists to explain something called action at a distance. I won't say any more about that, just to give you the idea of it, and see if you can think of what these things are, and I'll post the answers for you next week. Okay, so good luck with the tutorial. And before I finish, there's one final slide where I'm going to show you some demonstrations of electric fields and static charges on my YouTube channel. So this is the simulation I'm going to use. It's something called PhET. I'll put the links again on a file so you can access them. I'll also put the links for the YouTube videos so that you can see me demonstrating the different charges, etc. Okay.